Hello, YouTube! We are students from Purdue's Organic Chemistry 262 class for chemical engineers. My name is Annie Peters.
My name is Ashley Foltz.
And my name is Jakob Paff.
And in this edition of Real Life Orgo, we'll be discussing the chemistry behind organic fertilizers.
A fertilizer is a chemical or natural substance added to a soil to increase its yield. Plants need nutrients to grow and produce fruits and vegetables, which plain, old soil usually lacks. The 6 macronutrients required in large amounts by plants are nitrogen, phosphorus, potassium, sulfur, magnesium, and calcium. Eliminate any of these elements and plants will display abnormal growth and deficiency or may not reproduce at all. The most popular fertilizers contain 3 of these major nutrients, nitrogen, phosphorus, and potassium, and they're therefore referred to as NPK fertilizers. Nitrogen in particular is very important, forming parts of proteins, hormones, chlorophyll, vitamins, and enzymes, and promoting stem and leaf growth. Too much nitrogen can delay fruiting, while a deficiency of it can reduce yields and induce yellowing of leaves and stunted growth. Add just the right amount and you get a nice healthy growth like you see here. Now to talk about inorganic versus organic fertilizers. Ask most any gardener whether they prefer organic or inorganic fertilizer, and there's a chance you'll spark a lively debate. However, if you could ask your plants the same question, you'd find out that at the most basic level, they really can't tell the difference. Nutrients are nutrients. To begin with, the terminology can be confusing, since labels and gardeners freely throw around words like organic, natural, inorganic, or synthetic. But fertilizers can be reduced really to either inorganic or organic. All fertilizers supplement the soil with the 3 macronutrients mentioned before: nitrogen, phosphorus, and potassium. However, organic and inorganic fertilizers do so via different materials. The meaning of organic here in this context is different than our chemistry definition of organic. Organic fertilizers contain only plant or animal-based materials that are either a byproduct or end product of naturally occurring processes, such as leaves, compost, and manure, which we will focus on later. Inorganic fertilizer, also referred to as synthetic fertilizer, is manufactured artificially and contains minerals or synthetic chemicals. For example, synthetic nitrogen fertilizers are typically made from petroleum or natural gas. Phosphorus, potassium, and other trace elements in inorganic fertilizers are often mined from the earth. Balanced inorganic fertilizers, high in all 3 macronutrients, commonly include products like ammonium nitrate, ammonium sulfate, potassium chloride, and magnesium sulfate. Organic fertilizers are preferred because they don't contain potentially harmful chemicals and salts that inorganic fertilizers created in refineries do, but inorganic fertilizers may be preferred because they're lower in price and fast-acting.
Organic fertilizers are commonly created through several means. Farmyard manure is typically created from the feces of farmyard animals, such as horses, cows, and chickens, which is then mixed with other organic materials such as hay. A slurry is a type of manure typically made of manure and other organic matter as well as water. This is commonly called liquid manure, and slurries typically have the same organic chemical makeup as regular farmyard manure. Sewage sludge is created by taking sewage that contains human excrement and water and treating it in a sewage plant. This was common for a while, especially in Europe, but has since died down due to ethical and safety concerns. In the 2015 film The Martian, Matt Damon uses the leftover human feces when he is left on Mars to grow potatoes to help him survive, as seen in the beginning of this presentation. Compost is a 4th example of an organic fertilizer. It is created by allowing the decomposition of organic matter, commonly from plant, food scraps, and others. This often takes a while for everything to break down, but when it does, it creates a widely used fertilizer that helps in the addition of humic acids and nutrients important to plants. Now to get more into the organic chemistry side of things, we're going to talk about EDDHA. Iron is an essential micronutrient for plant growth, and despite being one of the most abundant elements on the planet, it is often the first element to become growth limiting to plants like algae due to its physical-chemical properties. Micronutrients, like iron, are very open to oxidation, precipitation, and other reactions in the soil or air. Chelating agents such as EDDHA helps protect these micronutrients so that plants can receive them in efficient amounts. Without EDDHA, most of the micronutrients, such as iron, and fertilizers are converted into insoluble salts that are of no help to plants. So what is a chelating agent? A chelating agent is a multidentate ligand, meaning its molecules can form several bonds to a single metal ion. In this case, EDDHA forms bonds with iron. When it forms, EDDHA presents two isomers, a para and an ortho. Iron can form 6 bonds, but the para isomer can only form 5. So the ortho isomer of EDDHA bonds with the iron. EDDHA is produced through the reaction of phenyl, glyoxylic acid, and ethylene diamine, in which the Schiff-based condensate alkylates the phenyl. Its IUPAC name is a mouthful: 2,2,2-hydroxy-1,2-hydroxyphenyl oxoethyl amino ethylene amino 2,2-hydroxyphenyl acetic acid.
Now, let's talk about the chemistry behind manure, a common organic fertilizer. Manure is made up of many common compounds, including organic nitrogen, ammonium, and urea. Once the manure is applied to the soil as a fertilizer, the urea converts to ammonium ions, commonly ammonium nitrate, through intermediates of toxic ammonia and carbon dioxide. The toxic ammonia is converted to ammonium through the addition of nitrogen over the course of a few days. The ammonium ions allow effective nitrogen to be used by the plants as nutrients in the fertilization process. A large amount of carbon present in manure are in the forms of proteins, fatty acids, lipids, carbohydrates, cellulose, and lignins. Organisms in the soil mineralize the carbon to either carbon dioxide, which is emitted to the atmosphere and then used in the photosynthesis process, or the carbon is bound to the soil as humic acid. Humic acid can be extracted and found productionally from cow manure, food waste, and paper waste through vermicomposting, a composting process that utilizes various types of worms, in which an alkali acid fractionation occurs. Fractionation is a separation process that isolates components in a mixture. The lignins in the manure or waste are then attacked by microorganisms in the soil to form phenolic aldehydes and acids, which either oxidize to carbon dioxide or convert to polyphenols. Cellulose and other substances from the manure react with the polyphenols and enzymes to form quinones, a 6-carbon-ringed molecule with 2 carbonyl groups, which then react with amino compounds, which include amino acids such as ornithine, histidine, arginine, and lysine, to produce the humic substances humic acid and fulvic acid. Both acids are humic substances. Humic acid also acts as a chelating agent similar to EDDHA with minerals, especially iron, phosphorus, potassium, and calcium in the soil. This allows the plant roots to uptake and utilize those nutrients more effectively. Through the chelation process, toxins in the soil are reduced in availability, while the minerals are increased in availability because of their now organic status. Humic acid also increases water infiltration and water capacity of the soil, while improving the soil, increasing plant root growth, and helping plants deal with environmental stress by regulating the pH level of the soil. Humic acid affects plant growth and soil efficiency physically, chemically, and biologically. Chemically, the acid regulates the pH value of soils by neutralizing acid and alkaline present in soils. It also enriches the soil in organic and mineral substances and liberates carbon dioxide from the soil that enables it to use in photosynthesis. And with that, we have reached the conclusion of the real-life Orgo edition of Organic Fertilizers. Thank you for listening to our presentation.